Okay, so today I'm going to continue with the concept of stability, and we'll try and put a little bit of math to it instead of just talking about it. If you recall, the intuitive notion of stability is something like a cone, and we have this notion that it's unstable if it's on its point because a slight disturbance causes it to fall, which is unbounded. We have this notion of it being in a situation with infinite number of stable positions when it's lying on its side, and then this intuitively is the stable position. So we're going to try and quantify this a bit mathematically, but before doing that I wanted to give a sense of what does this mean, this multiple set of stability, and I want to do it in the context of the telephone network and the metastability condition as it's called. And the reason for doing that is, one is because it gives you some insight into how the telephone network works, and the second reason for doing it is to explain an important concept, which is that just because a system is in a stable state doesn't mean it's a good state. You can have a bad stable state as well. So it's good to be stable. It's better to be stable when it's in a good stable state. Being in a bad stable state is not a great idea. So I think that's what I want to convey. So let me just set it up by showing you what the telephone network looks like. So most of us use cell phone network, without really thinking about what's going on under the covers, so to speak. And what I'm going to show you is a very simplified view of what it is. But typically in each country you have this notion of local areas, and I'm just going to draw a cloud corresponding to each local area. For example, this corresponds to what's called the area code. So 519 is the area code that corresponds to this local region, and that would be one area. And I'm not going to show you the structure of that area actually, because that's not relevant. However, the different areas in any country are actually connected in the form of a logical clique. So essentially every area is connected to every other area by one hop line, and so on. So this is conceptually this is the way it's done. So physically, of course, it's not a complete clique. Physically it's done with physical lines, optical lines, and so on. But but every area code, let's say this is area code 416, which is the Toronto area code. Essentially 519, when it gets an incoming call, so you dial a number saying 416 something something something, 519 is going to go send that call and eventually all the data on that one hop path. Okay, it's not going to do any complicated routing. It's just going to say, oh, it starts with 416, it's not for me, let me go find the output port that corresponds to 416, and off it goes. And the reason why the routing is particularly simple like this is because this was done in the days of electromechanical switches in the old days, and it was done before computers. So this was the kind of routing that was invented in the 1920s, 1930s. Of course, as the system progressed and there were more computers and so on, more complicated routing schemes could be envisioned. But that was done in the layer underneath. So from the perspective of the call forwarding, you still have this very simple notion of taking an incoming call, which is this message, call setup message that says send me to this destination, and it just goes to that it just goes there basically. Now, if you take a clique, routing is very simple, but it has one intrinsic problem, and the problem is that it's if all calls are being sent along the shortest one hop path, it is inherently inefficient. So if you look at this, let's say this is A and this is B, and this is taking the shortest one hop path. Actually, there are more paths. You could go like that, you could go like that, you could go like that. So there are at least 3 other paths that you could have taken, but you didn't, right? So what's going on is that we have this problem that the capacity, or the inherent capacity of the network, is being not fully used, okay? And so one could say, why are we doing this? Let's say that this A to B path is fully loaded, and let's say you're trying to call, let's say this is 519, and you're trying to call somebody in 416. Now you have 2 choices. Let's say the capacity is full. When a new call comes in, you could do one of 2 things. You could say, I'm not going to accept your call because all circuits are full, right? And you may have experienced that sometimes when you have your cell phone, you try to use it in a congested or busy cell, it says call cannot be completed, all circuits are full. So how many of you had that experience of having a call rejected? Or sometimes in a landline, you'll get this fast beep, 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 very fast, busy tone. It's called the fast busy, and the fast busy doesn't mean the receiver is unable to, it's busy, it just means that the network is congested. It happens very rarely. We design the network so that that's supposed to happen with the probability of less than 1 in 10 to the minus 6 roughly. So once every 800 years, you should be experiencing that. But it still happens. Anyway, instead of doing that, instead of having this call, we could say, hey, wait a minute, why don't you just send it on a 2-hop path? Because there are lots of 2-hop paths, okay? And so then you don't need to use 1-hop path, but you have to be clever about it. You have to be a little bit more clever than just sending it only on the 1-hop path. So in the case of the electromechanical switches, you can only do 1-hop paths. But the computing based call forwarding came around 1961 actually, and at any rate, this is what is done today. You do actually have these 2-hop paths going like that. So that's why we have very little call blocking, because we can do this. But this introduces a problem. So to understand this problem, what we want to do is to understand let's say this AB path is busy. Okay, and if the AB path is busy, what happens is that we're going to send that onto the other path. Now here is where things get interesting. So if we have this other path over here, and here's this 2-hop path shown in green like this, what's going on is this path now has additional load on it. Okay, so in fact, if you think about it, every 2-hop path puts twice the amount of load on the core network, okay, within the 1-hop path. So we're sort of doubling the load. And of course, it's going to have negative consequences, because if this path over here is also busy, so you can't send calls from here to here, then this 1-hop path is going to go to, or maybe let's say take this one, let's say, okay, this gets messier. If I take this path over here, this might decide to go like this in blue, because that 1-hop path is busy, so it's going to go like this. It's going to take a 2-hop path as well, okay? And then maybe this one is busy, so that's going to take a 2-hop path. So that's going to go, who knows, some other way. It's going to take this 2-hop path instead. So what happens is that if this network is highly used, then a small disturbance is going to cause this domino-like effect where all these paths are going to get pushed out, and you get everybody taking 2-hop paths. And the interesting thing is, and people have studied this both in practice and in simulations, is that when the load goes down again, goes from high load to low load, these 2-hop paths persist. So you have a heavy load, you have a little bit of extra injection of traffic into this AB path, and then it flips traffic over, that flips more traffic over, that flips traffic over, and then suddenly everybody's doing 2-hop paths, and reduce the load, they stay in 2-hop paths. Because what's happened is it's just like this cone over here. So you tip the cone a little bit, and it actually goes in a different stable position. So this 2-hop path is also stable, and it's called the metastable condition. Okay, it's just the name that they use in the telephone network, and it's a metastability condition. And so that is an example of a persistent or a stable bad state. It's bad because everything is taking twice the amount of work that it should. You could do everything in 1 hop, but you're doing it in 2 hops instead, so it's taking twice as many resources. And so quite a bit of work was done in the telephone network to try and ensure that this didn't happen. You were kicked back into the regular state. And the solution turns out to be reserving some capacity of this only for 1 hop path. So when you go over here and you fill up this path with traffic that belongs originally to 1 hop path, you cannot use it all up. You can only use some of it up. Same thing over here. So when the additional traffic comes, it would not be tempted to go down and up again because there would be a little bit space left on this for the 1 hop traffic. And by just doing the small amount of reservation, which is about 5-10%, you're actually able to prevent this unstable condition. So in designing a system, we need to be careful that the good states are stable. We also need to be aware of stable bad states and somehow put rules for operation or control mechanisms such that you're going to be coming out of the bad state into the good state again. So be careful that you don't end up in a stable bad state, and there is a way to recognize you're in a stable bad state and say, okay, I'm going to avoid it. Okay, so that's sort of the rule, design rule over here. Okay. The other thing that's worth looking at is to see that is this system BIBO stable and is it zero input stable. So again, let's look at the bounded input, bounded output stable condition. So we have to sort of define what is the input and what's the output of the system. And for computer networks, you can usually define the output in two different ways. So one output could be what's called carried load. Means what are you carrying compared to, so you're giving some input load, traffic, bits per second, or the aggregate bits per second. What are you carrying? That's the output. And then the other output could be the sum of the buffer occupancies. And the buffer occupancy being some kind of just the integral of the carried load, okay? And so you can view that as a buffer occupancy. And if you do it in this way, it's kind of funny because basically if your network is working fine, then your buffer occupancy should be fairly low. So as the input load increases and increases, your output actually is zero. Okay, but at the point where you have some congestion, the output increases. So it's a different kind of modeling, and this is useful sometimes. This is useful sometimes. At any rate, if you just use this one over here as the carried load, then let's look at the BIBO stable criterion. So we define the equilibrium state to be a network which is idle. There's nothing going on. And that's intuitively, that's a stable state. There's nothing going on, no input, no output. We get a little bit of input. For pretty much any network, as long as the amount of input rate is fairly small, what's going to happen is that it's going to be carried. Okay, the output is going to be proportional to the input, and we're going to get what you can think of as BIBO stability. Okay, and so with the unless you have a routing loop or an email loop, something like that, the output is always going to be proportional to the input. So a well-designed network, well-designed operational computer network is pretty much defined to be BIBO stable. For zero input stability, well, if you look at zero input stable, what we're saying is for all possible input rates, the output rates are going to be going to the zero state. So when you look at the input, zero input, essentially input state, if there's nothing going on, no additional traffic is coming in, all we care about is packets in transit. And again, without any loops, it's all going to go away. And especially if you have the time to live condition, we know that even if there are loops, the time to live is going to have the packets be deleted after some point in time. So the TTL is going to essentially guarantee zero input stability. So it's a blanket statement to make, but you can claim without too much exaggeration that essentially any computer network without loops, or even with loops with the time to live feature, is going to be both BIBO and zero input stable. This is going to be true, of course, for the telephone networks as well. The telephone networks really are just a special case of the computer network. Okay. And so the main instability I'm worried about in these networks is basically oscillations, and which we think of as marginally stable. And we really have to worry about oscillations because they're inefficient, and we can view them as being a bounded stable or marginally stable condition, which is inefficient. We try to avoid it. Okay. So any questions about this? This is basically what I'm covering in examples 14 and 15 over here. But I'm just trying to give some sense of how do these concepts of stability, which are fairly abstract, relate to operations in real networks. And so the two things that are practical, one is the time to live field, and the second thing over here is the reservation of some capacity for one-hop paths. These are two practical outcomes that come from the concept of stability. Okay. Any questions here? Okay, so let me now set the stage for somewhat more mathematical understanding of a LTI system. Now, networks are hardly LTI, They are neither time invariant nor linear, but again, we can use the insights. So we'll start with the time domain equation for a LTI system, where we say yt, the output, is given as essentially the convolution. I'm just going to explicitly write out the convolution of the system impulse response in the time domain. Okay, so R is your command or the input into the system, G is the plant and the time domain impulse response of the plant, and we know that the output Y is going to be the convolution of the input R with the impulse response G. So this is the standard equation over here, right? So nothing new here. This is just the time domain modeling. So we want to know when is Y bounded. Okay, we want to know how to bound Y, and so we so what we're going to do over here, and we can actually replace this with 0 over here because it's a causal system. We don't really need to worry about anything less than 0 because we're going to have command equal to 0 when we have a time less than 0. So you can already, or we can do that over here. So we want to bound yt, and so the bound of yt is given by the bound of this integral 0 to infinity g tau r e minus tau d tau, and we can always show that the absolute value of the integral is always going to be less than equal to the integral of the absolute values. Okay, so it's going to be less than equal to mod and g tau. Okay, and this just it's fairly intuitive that the absolute values are always positive, so you know it's going to be the case that this is always going to be the case over here. And if the input is bounded, then this is going to be less than some value R max. So this is going to be less than equal to R max, the maximum input, integral 0 to infinity. Okay, and we can just replace tau with t because it doesn't really change anything to do that. So I can just look at gt dt. So what does this say over here? It says that this is, so we're looking for BIBO stability for a LTI system. For a LTI system, the bounded input gives us the value that the input is less than some value R max in magnitude. And so this one, the output is going to be bounded when this integral is bounded. Okay, mod gt dt is bounded. Okay, what we really care about is that the that this value of gt, the impulse response of the plant in time domain, does not explode. Okay, what we're saying is that we don't really care what the input is. Okay, we don't really care for Bibo instability. We just are going to model the input as being bounded by some value R max, and all that we care about is the magnitude of the impulse response. Okay, so if the impulse response is unbounded, then we know it's not going to be Bibo stable. Okay, so we have managed in this little derivation to completely basically eliminate the command RT minus tau by just saying it's bounded. Okay, because we care about bounded input. So the focus becomes now purely on the plant, on the control system GS instead, rather than looking at the whole range of all possible inputs, which would have been much more complicated. Okay, so that's really what's going on over here. So the math is saying, okay, we can essentially assume that the input is the maximum possible, is R max, and we'll still show that R is bounded because it's going to be this multiplied by this. Okay, so we makes life much simpler. We just need to look at the plant, and okay. So to look at the plant, instead of looking at the time domain GT, what we're going to look at is basically GS, its Laplace transform, and see what the Laplace transform looks like. Because it turns out it will be much easier to look at the Laplace transform, and of course this is the transfer function. So we look at essentially just the transfer function and see what it's doing, and from the transfer function we can figure out what the impulse response is going to be. From the impulse response we can figure out whether it's BIB or stable. Okay, so that's the logic going on over here. So, any questions about this here? Okay, so to look at this, there's a couple of kind of facts we want to throw in over here. The first one is the transfer function form is going to be form for an LTI system that is expressed as differential equations. Okay, is going to be a ratio of polynomials. And actually this is very easy to see, and I'll just show you why. Because we know that if you have something that looks like, you know, xt or x dot of t, so xt goes to some function x of s, then x dot is going to s x of s, and integral of x dt is going to go to xs by s. So all the derivatives just become polynomials in S. Okay, integrals become ratios in S. So basically, it's all just S, S squared, S cubed, and so on. And if you remember, the general linear time invariant equation is basically y to the n. You know, we had this. Actually, if you remember the differential form, it was d to the m or d to the n plus d to the something a d to the n or a1. Oh, okay, I'm going to get confused with the something d to the n minus 1 plus something d to the n minus 2, etc. y, okay, equals d something something of x, right? That's the differential form we studied when you're looking at the general LTI system. All these guys just become a s to the n plus b something s to the n minus 1 plus something something. So all powers of s. And the right hand side is also powers of s. So if you take the ratio of output to input, right, which is the transfer function, it's going to be just polynomial ratios because it's all powers of s. So that's the beauty of the transform. It's converting differential equations into just polynomials in s. Okay? So then we essentially find that the GS can be written as some b0 s to the m plus b1 s to the m minus 1 plus so it's going to be some polynomial ratio like this. And when we see a polynomial ratio like this, immediately we say, oh, wait a minute, let's try and factor that into its factors, because you can then use partial fractions. And so that's going to look like a bunch of terms, and I'm going to talk about the terms after the break, but it's going to be basically s minus alpha 1, s minus alpha 2, etc., where we have to be careful because you could have complex roots, you could have repeated roots, or you could have distinct roots, and you have to worry about each of them separately. Okay, so stop here, but I just want to go through logic one more time. So we start with the time domain. We're going to look at bibostability for LTI system. We start with the time domain, which is going to be true for any LTI system. We're going to compute the magnitude of the output, which is bounded by this. And then we pull out this part as being smaller than some R max. And then we want to look at this integral of the impulse response, or the magnitude of the impulse response. And we're going to qualitatively, at this point, argue about what this integral is going to look like based on the transfer function, saying that the form of the transfer function is going to be a ratio of polynomials, because we're basically going to convert all the derivatives and higher order powers, higher order derivatives of x and y into just multiplication with s and s squared and so on. And when we do this transfer function gs that we care about is going to look like this. And you can then express in some form of partial fraction expansion like so. And then this will go, when we go back into the time domain, it will allow us to determine what that mod gt is going to look like, the integral mod gt is going to look like. Okay? Yeah?
So if m is greater than n,
yes,
then you will get some more terms as well, s to the power m minus n.
Let me try and answer your question here. So if you have m greater than n, then we can always do the polynomial division, right, of one polynomial by the other. So we'll have some polynomial plus the remainder polynomial, okay, over this, right? So this will be some polynomial in S, which is the just doing the ratio division, polynomial division, and so this will have terms like, you know, S to the whatever k, or actually it will be in this case m minus n plus S to the m minus n minus 1 and so on. Okay, so we're going to then take the inverse Laplace to get in the time domain, right? So the question is, what do these look like in the time domain? So we know that basically delta goes to 1 and then let me see, what goes to S? Beg your pardon?
Derivative with respect to
Yeah, so we're going to take the derivative of delta, so that's not so good. Yeah?
We can rewrite GS as a S to m minus n multiplied there.
Right.
Okay, so we can think that it is deviation of another GS that is exponential.
No, I know, I mean, yeah.
At first, factor S to m minus n.
Yes.
Multiplied
By this whole thing over here, yeah?
Yes.
Sure.
So deviation of this part.
Right.
This part is exponentially.
Right.
And we can make a derivation in time domain from exponential.
So you're saying this is going to look like S to the m minus n times some ratio of polynomials. And then this is going to be, then the time domain is going to be,
Deviation of that part.
well, there will be some expansion of this, right? You can expand that. Okay, so it's going to look like some set of partial fractions. Okay, it's not one, there's something else over there. Okay, and multiplied by this. Okay, but then I'm trying to remember what the inverse Laplace is going to look like for.
Okay. X prime equals to S multiplied XS.
Right.
And the Laplace inverse transform of that part is
Right.
exponential.
Yes. Yes.
We know that.
Right.
So just we should.
Yeah. See. So this is going to be y. This is going to be d to the m minus n y by d y dt to the m minus n, or whatever you get over here. This is going to be yt, I guess. Right. So that the inverse helps, and so we can find the derivatives of all those steps. Okay, that would work. Yeah. Okay. Yeah, that's good. So just to explain what's going on, if m is greater than n, which is actually in practical cases we won't have it, but let's say we do, we can just pull out the factor s to the m minus n over here, and then basically all these ratios will go down by factor of s to the m minus n. So then you get some polynomial over here which is of equal or smaller value than this, like this. And then this will expand using partial fraction, as I'll show you in a minute. And once you do that, we're going to, this corresponds to, if you do, we can expand each of this separately term by term, because the Laplace transform is linear. We can expand this each to the term, and then we get something that says s to the m minus n over some value over here. This s to the m corresponds to the m minus nth derivative of some value, right? Because we have some x dot corresponds to this, so we can then invert that to find what the y is going to be. Yeah.
we can't like pull out s to the power m minus n, because we'll have like bm s to the power minus of m minus n.
So we can take this one as this separately, right? When you do the partial fraction expansion, you always write s to the m minus n over something. Okay, and we can view that as being, you can view this as being the derivative of some other function of time. Okay. All right, so let me look into it, and maybe I should get back to you instead of doing this on the fly. So m greater than n. Okay. So the explanations I've seen in the textbooks, since I'm not an expert in this area, I can just tell you what the textbook says. In practice, it doesn't happen, so forget about it. Okay, that's what they say. But maybe if it does happen, I need to look into what you actually have to do. Our problem, generally speaking, when we're talking about computer networks, is that the system is not even linear. So even LTI modeling is a bit of a stretch. But this is certainly an interesting thing to look at, and I'll get back to you. Yes, that's it.
Yeah, something to take into consideration is that systems which have m more than n are not realizable.
They're not real.
Actually differentiating, and you can build a differentiator which differentiates from all the frequencies. You have to have an upper limit on the frequency. So actually, you cannot build a differentiator. That's why in control theory, you always say that n is greater than equal to n.
Yeah, so I mean, as I said, this particular case doesn't arise in practice, right? But from a mathematical perspective, it's certainly interesting to see how do you deal with this. Even if it's not something that arises in practice, which is what I said, the textbook basically says it doesn't arise, and you're giving me a practical reason why it doesn't arise, because it's not realizable. Still, mathematically, it would be interesting to know how to invert this. And I think I'll look into that. But, thank you. Okay, to come back to this, when we have this kind of polynomial ratio, what we're essentially going to do is to convert this into partial fractions. And as you will know from reading that section on partial fractions, we have basically got a bunch of terms over here where the terms fall into three categories. One is distinct roots, which is the easiest case, and then we have second case of complex conjugate roots, and then finally we have this notion of repeated roots, which could be complex or could be either repeated roots, which could be complex. They can be complex conjugate. So let me first talk about distinct roots, and then I'll talk about the complex conjugate and repeated roots. So if you have distinct roots, then we have the situation that the term looks like some value a over s minus alpha I, where alpha I is the distinct root. And this is going to correspond in the time domain to a e to the minus e to the plus alpha I t. So s minus goes to a to the e to the plus. And so we get the situation where if alpha is going to be in the left half of the complex plane, like this, okay, some point over there, because alpha could be, sorry, it's not complex, it's real. So oops, right, so alpha is going to be, right, distinct, I should say real. Okay, so alpha is in the left half of the plane. We get a to the minus alpha t, and that's going to be exponential that goes down. If alpha is on the right, it's going to be going up. And if alpha is at 0, we get a constant. Okay, so let's see. If it's going up, then this integral clearly is going to be large, and essentially it's going to be infinite, and so it's going to be Bibo unstable. Okay, because you give it a small input whose value is R max, but the output is going to infinity. So that's not good. If it's on the left-hand side, then we say, sure, it's going to be bounded. And if it's at 0, the integral is still infinite because we have some constant value integrated over to infinity, so it's infinity. So the stability condition basically becomes alpha I should be strictly less than 0 is the stability condition. And we get that from this right here, okay, and the understanding of the complex exponential, which is why I said, in the beginning, the complex exponential signal is at the heart of control theory. If you understand what it's doing, you understand how this whole thing is working, okay. So distinct real roots is the easy case, okay. Any questions about that? Yeah. So let's look at the next one then, complex conjugate. Why is it conjugate? The reason is because when you have a real system, it will turn out that these coefficients are all going to be real. Okay, when these coefficients are real, the only way to get sort of two complex numbers to add up to a real coefficient is when they're conjugate. Again, you can try it out, and you'll see that if they're not conjugate meaning they look like a plus minus jb, we have to have plus minus jb, then you won't get real coefficients, and these are known to be real coefficients because it's a real system. So real system means real coefficients. Real coefficient means that the the roots are going to have to be conjugate. And so in this plane over here, if I were to draw A plus minus JB, it's going to be basically pairs that are above and below the real axis like this. Okay, like I've shown 3 pairs over here. They're going to be the same